This is the second review on integral theorems. Here are three heroes who were working on these theorems. And today I want first to start with a little bit an overview over the objects which we are dealing with, and then pick up where we stopped yesterday. We start with triple integrals, and especially in different coordinate systems. And then we look at vector fields, line integrals, and then come all the theorems, the four important theorems, which is the fundamental theorem of line integrals, Green, Stokes, and the divergence theorem. And in the end, I want to say something about strategies to figure out which theorem to use. You will have to use them as like keys for opening doors, and sometimes it's tough to pick. They look all the same, right? To pick the right key, and but they are important, and there will be 60% of the exam essentially covers this material here. So that's the plan, and so here is a slide which features all the objects which we deal with. So we deal with objects in the plane or in space, like vector fields. This vector field in the plane, vector field in space, or region in the plane, or curve in the plane. Curve can also be in space. And then in 3 dimensions we have the solids and surfaces. And so it's a very rich arena for geometry. And the integral theorems deal with these objects. So it's good to know with which object you work with. And maybe to organize this a little bit, one can organize this like that. They are all functions which map a function of one variable, takes a variable and spits out another result. So that's what you have learned in single variable calculus. Now in multivariable calculus, we have looked at curves. These are vector valued functions of one variable, or here also curves in 3 dimensions where you have vector valued functions. So vector valued means the target is 3-dimensional. And then in 2 dimensions we have functions of 2 variables. The target is 1-dimensional, a function of 3 variables. And then we have vector fields which in the plane take 2 variables and spit out 2 variables. And in 3 dimensions you have x, y, z, and you get 3 numbers at every point. And then we have also the surface, which just takes 2 variables and maps us something and gives us something in space. This is the parametrization of a surface. We didn't talk about this thing. That's maybe more in linear algebra. You look at these things. And also in linear algebra, you look at arbitrary maps from any space to any other space. But so here, these are the objects just organized according to dimension. You have also seen that we have a lot of matching problems. Also, now we will do some matching, and in this slide is essentially what you can come up with what you can match. Essentially, everything we look at, they are just always 1-dimensional, 2-dimensional, 3-dimensional things. We have curves, surfaces, and solids. So curves are 1-dimensional, surfaces are 2-dimensional, solids are 3-dimensional. Fields, you have scalar fields, which, or then we have vector fields in the plane or vector fields in space. But we have derivatives. We have the gradient, the curl, and the divergence, these 3 derivatives. And they are paired with integrals, line integrals, flux integrals, and triple integrals. So each of these pairing here will produce a theorem. This will be the fundamental theorem of line integrals. This is the Stokes theorem, and this is the divergence theorem. And in 2 dimensions, we have just 2 theorems. We start with triple integrals. So just something important about setting up the triple integrals. It depends on the coordinate system. If you have a Cartesian coordinate system, this is by far the most common situation, where you have a kind of a bottom part and you have a top part, like a floor and a roof, and you integrate over some region. This region is here drawn out. So this is what you integrate over in 2 dimensions, and then you go from the bottom to the top. So you know spherical coordinates. We have looked at yesterday already at this parameterization of a sphere, right? That's a parameterization of a sphere of radius rho, but rho is now an additional variable, and you have this integration factor, which you should not forget when you go into spherical coordinates. If you go into cylindrical coordinates or polar coordinates, you have this factor r. Also this factor, don't forget that. Let's look at this problem. So it's the first problem here. We have a kind of a cone, but it's not just a cone, but it has a kind of another cone on top of it. And so we have a function fx, y, z, which we integrate over that solid, which is given here with these inequalities. Possibility to do it. The other possibility is just to integrate over the shadow, and so integrate over the disk, and then go from the lower function to the upper function. It's the second problem, and I want to go through with this computation. So we have, again, a volume problem, but we have an intersection of two surfaces here, two paraboloids. We want to set up the integral here again for this problem here. So this is r, and this is c. And so what is given? So r is equal to 9 minus c squared. How does that look like? So r is equal to 9 minus c squared. So think about this as kind of, if you look like that, so you see at z is equal to 0, we get 9. And then we have a parabola, which is going 9 minus c squared, which goes like that. And this is the first parabola. So this is r is equal to 9 minus c squared. And the second one is r is equal to 1 plus z squared. Let me just see, look at that here. 1 plus c squared, where does this intersect r? The r-axis, if c is equal to 0, we get 1, so that's, and then we have a parabola which goes like that. So these are the two paraboloids, and we intersect these two, or these two parabola in this picture, and we then rotate this around. So we have this region, and you kind of see how this looks like when we rotate this around. So this was z is equal to, r is equal to 1 plus z squared. Now what we want to do is we want to see how to set this up. How do we integrate here? The theta coordinate is no problem. We just have some 0 to 2 pi d theta. That's there because we rotate around. The theta doesn't appear in the description. But we have to set up, we have to integrate over this region, and that's now just a double integral. So if you look at the double integral, it's always important to think about, is it a type 1 integral or is it a type 2 integral? In this case, it's both. You see, you can actually look at this, both works. But there is one which is smarter than the other. And if we go from as a type 1 integral, we would have to split this up. Would be possible, but as a type 2 integral, it's much better. And so as a type 2 integral, we first integrate in the z coordinate, so the z coordinate, and now we have to figure out where do we integrate over, from where to where. What is the range here? From where to where do we integrate? And in order to figure this out, we have to make the intersection of these two. So we have to look where they intersect, and so 9 minus c squared is equal to 1 plus c squared, and we put it on one side. So we have 8 is equal to 2z squared, 4 is equal to z squared, and so we see that c is equal to plus minus 2. So these are the question mark becomes a 2, and so this is our interval here we integrate over. Remember, type 2 integral is a left to right integral. We have the left and the right. So the left goes from, we have a picture that helps us to make this thing. It's not my day. So minus 2 to 2. Yeah, that's the z coordinate. That we have done that. The third integral, we don't even have to, we don't even need that here. We can just plug that in here. We have now from the left curve, which is 1 plus c squared, to the right curve, which is 9 minus c squared dr. And we want to compute the volume, so that's the function 1, which we integrate. And we have coordinates, we have polar coordinates in the polar coordinates, and so we have to put that r here. Is it now correct before we continue? Does it work? So that's the integral, and let's just compute this integral quickly. So we integrate with respect to r. That gives us r squared half minus 2 to 2, and then we have r squared half evaluated from 1 plus c squared to 9 minus c squared dz d theta. And now we plug that in here, so we get 0 to 2 pi minus 2 to 2, and then we get 9 minus c squared square minus 1 plus c squared square divided by 2 d z, and then d theta. So that's not a problem. Now we can just factor this all out and integrate, and I'm not doing that. That's just something you can do, and the answer is 640 pi third. So that's the answer. The first who has the answer, shouts the right answer, gets the chocolate. So 3, 2, 1, and 0. What is integrate this function over this solid? No, not solid. That would have been an easy chocolate. 2 pi is also not right. It's a good choice. I mean, often things are pi or 2 pi or what? No, not 28 pi. Just make the computation quickly. We will actually do it. We will do it then right away.
3 pi?
Nope.
42 pi?
Who had 42 pi? Cool, wonderful. That's right. Congratulations.
All right. The answer to the ultimate question of life, the universe, and everything is 42. Yes, I thought it over quite thoroughly.
No, you have not seen that movie, Hitchhiker's Guide. 3 important rules. Use the right coordinate system, absolutely crucial. And the second thing is that also you might want to change the order of integration. Don't forget that in case something cannot be solved directly, or kind of use type 1 or type 2, whatever is better. And the third one is also make a picture of the region you integrate. So that's about integration. Let's look at vector fields first. So in 2 dimensions we have essentially 2 derivatives. In 3 dimensions we have really 3 derivatives, like 3 integral theorems. There's the gradient, the curl, and the divergence. The divergence gives you a scalar function. The gradient gets you from a scalar function a vector field, and the curl, that's the only thing which takes a vector field and spits out the vector field again. And in this case, this is kind of an example which I have mentioned last time already, an important example where one can really see the curl. The curl goes here upwards, so the vector field turns around, and so the curl goes upwards. There's a theorem which says every textbook in multivariable calculus has a paddle wheel, and I made them once a collection. All these are all the textbooks which I could get the hand on, and they all have a paddle wheel. And this paddle wheel kind of explains, that's my favorite book, by the way, this one, How to Ace Calculus. It's a fantastic book. It suggests to the teacher to show the paddle wheel off in class with a paddle wheel and stick it in the finger. So, pretty funny book. So, paddle wheels were also kind of honored in the science center. I don't know if I remember in September, October, I made that picture. But they are still around, these paddle wheels. So there is this one here in the Soldiers Field the garage, and one on the Holyoke Center. There are a couple of paddle wheels, just to remind you about multivariable calculus. So line integrals, that's an important integral. So there are three integrals which we in every dimension. The first one is the line integral, which integrates over a curve. And you should think about this as force, and this is about velocity, and this is power. And if you integrate up power, you get work. And so think about this is work done by. So there are integral theorems which deal with these line integrals. One is in 2 dimensions, it's Green's theorem. In 3 dimensions, it's Stokes' theorem. And in 3 dimensions, it's also the fundamental theorem of line integrals. So there are the fundamental theorem of line integrals also in the plane. And then we have the second important integral, which is the flux integral, which takes the vector field, evaluates it on the surface, and multiplies with RU cross RV. And this measures how much fluid goes through the surface in unit time. So one thing to remember, this is a triple scalar product, so this is a volume. And if a volume of this parallelepiped spanned by this vector and this parallelogram, so this tells you how much has gone through the surface when you go from the bottom to the tip of the vector. And so it's pretty intuitive. These are really the integrals which we know. And then the triple integral, of course, which we have already covered in the first section of this lecture. But these are the 2 integrals which we deal with. The first is the line integral, and the second is the flux integral. So this deals with curves, and this deals with surfaces. And for curves, we have a velocity vector. For surfaces, we have the normal vector, which is RU cross RV. So this is all you need. So now we come to the integral theorems. I want to go through these 4 integral theorems and solve some problems on this. The first theorem is the fundamental theorem of line integrals, which tells that if you have a gradient field, it's much easier to compute the line integral. You just evaluate the potential at the endpoints, and this f is the potential, that is the function which gives you the vector field. So it's important, maybe take this always, whenever you see a line integral, first ask yourself, is this really applicable? You know, can you really use this fundamental theorem of line integral? Whether the curl is 0. The curl is 0, then this is a gradient field, and you can find this potential. So that's the first theorem. And by the way, the proof is very easy because you can actually see it here. This is by the chain rule, just the d over dt f of r of t, and then you use the fundamental theorem of calculus. You get that. People have built actually nano motors and nano cars, and it's pretty amazing. Everything gets so small. But what we have is, so this is actually a picture.
Consisting of a single molecule, just 3 to 4 nanometers across. They are slightly wider than a strand of DNA.
So this is a nano car. Let's look at the problem. So we have a force field is given, and the car is pushed along some curve. And the t goes from 0 to pi. What work is done on the car? So the question is, what work is done on the car means what is the line integral when you integrate along this curve. Now, if you are naive, you start integrating, right? Putting in x and y and z. X, you throw it in here. Y, you throw in here. Z, you throw in here. But then you get you get integrals which involve cosine of thing. Sine is very complicated. You have no way to do that. And but then you think, oh, maybe this is a gradient field. And indeed, this is a gradient field. Maybe you can see it. I made it simple. So can you see what the function is? Negative sign, positive sign, and then let's just try that. And then we take the fx. Oh yeah, that works. Fx is cosine x, y, z, so that really works. The gradient of f is equal to f. But let's suppose we don't know that it is. Maybe you cannot see that. Needed some intuition to see that. But what you have is you have an equation which says, so suppose we don't know, and say we have fx is equal to yz cosine xyz. And when you have this equation, you just see that f is the integral here. So f is, you have to integrate that. And actually, it just works out. So already here, so that's x, y, z, that already works, plus a constant. And when you do that, which can depend on y and z, and then what you do is you take the derivative with respect to y, which is xz cosine xyz, and then plus cy yz, and that's equal to xz, because the problem tells you what fy is, cosine xyz. And now you see that cy is equal to 0. And then or it's actually just a function of z only. And then you take the derivative with respect to z, and then you check that fc is equal to, what is that? Is equal to y, xy cosine xyz plus c prime z, and that's xy cosine xyz. And then you see that then you see that c prime is equal to 0, so this is just a constant. So that would be the formal way, which you have practiced a lot. The formal way, if you don't see the integral, you don't see the potential, you can do it in a formal way by just integrating up. But here we have now this function, right? And so once we have the function, the problem is very easy. What we have to do is just take so we have to compute r of pi, right? We have to see where the car is at pi, and r of pi is just pi minus 1, 0. And then r of 0, that's the second, that's the initial point here. That's then 0, 1, 0. And so we have the result is, please, even if you see that is the fundamental theorem of line integrals, please state that it's the fundamental theorem of line integral. So apply the fundamental theorem of line integral. And so the result is f of r of pi minus f of r of 0, which is evaluate the function sine xyz here. That actually is equal to 0. It's not very interesting. So this car has not done any work. So that's the nano car problem, which just used that fundamental theorem of line integrals. So there are some things which are equivalent. Just we had here a gradient field. That's what it means to be a gradient field. You have a gradient of a potential. This also means that you have path independence. Right? If you go along a closed path, then the initial and end points are the same. So the result is 0. Closed, actually, that was the closed loop property. Path independence means it doesn't matter, how you go from A to B, this car could go anywhere from A to B and always you would have to do the same work. And another thing which is equivalent if the region is simply connected, but that's usually the case, then this is equivalent that the curl is everywhere 0. And so these are the 4 things. And that's usually called conservative, all these things together. So the example which which you have, I think, seen is this example of a vector field which is not defined at the origin. And indeed, this vector field has curl 0 everywhere except at the origin. So the closed loop property doesn't hold here. But the reason is that the region is not simply connected. So there's a singularity at 0. But usually you don't have to worry about these cases. This is very singular. But maybe that's worth a chocolate. What is the line integral of this here? That's not so easy. What is the line integral of this path which we see here for this vector field here? Let me just tell you here, in this case, if you go along here, you actually have when x squared plus y squared is equal to 1, what happens here, the vector field has length 1 and is always tangent to the curve, so the line integral is just 2 pi. You can make the computation here, the line integral is just 2 pi. Now what is the line integral here? No, not 2 pi. Who said 4 pi? Why is it 4 pi? You go around twice. So every time you go around, you pick up. Very good. But that's not so easy to see, so that's worth a chocolate. Yeah, good. Yeah, that's a little bit advanced thing. So what happens, you can actually deform this path so that you go twice around this curve here, and twice you pick up 2 pi. So that was the fundamental theorem of line integral. Just remember, if you see a line integral, look whether it is a gradient field or not. So Green's theorem, very important. Green's theorem deals with vector fields in the plane. So this is a planar situation. We are in flatland. It's nothing to do in space. And unfortunately, there's no picture of Green, but he was a miller. So this is kind of a symbol for Green. And so that's a theorem, and it kind of measures in the plane measures what is the discrepancy when you go along a closed loop here. If the curl would be 0, then this would give you 0, but this formula is true, which tells you that the double integral is this line integral. And important is the direction, so this boundary is oriented so that the curve is always to the left. That's an important part. And there are 2 ways how you can use this theorem. One, you can use it to compute double integrals. Another way, you can use it to compute line integrals. And we do examples to both. So whatever is easier, you can. So this is a problem. I think you have done this I think in a homework or something similar. But here we have a problem where we want to compute the area. And so this is an area problem. Now, first of all, we have to get the curve here. We could actually give the curve. So if you look at this curve here, cosine cubed t, sinus cubed t, if you look at that, that's really on that boundary. Because if you take the cosine cubed t and take the power 2/3, you get the cosine squared t. And so cosine squared t plus sine squared t is equal to 1. So that's the curve that parameterizes the boundary. Now, the problem doesn't tell you anything about the vector field, so you have to kind of invent a vector field. What vector field do we take which gives us the area? 0x, that's a good one. So let's take that. So that's the simplest vector field which has curl 1. There are others like minus y x half. I think that would make it a little bit easier, but let's go with this here. And then we just compute the line integral. Compute the double integral of g curl of f dx dy, which is just the area, because this is equal to 1. And that's then the line integral from 0 to 2 pi f of r of t times r prime of t dt. So now we have just to compute the line integral. And it's actually a good opportunity. Practice a little bit integration and setting up the integral. See that like a circle that goes around from 0 to 2 pi. So we integrate from 0 to 2 pi. Then we take the vector field, which is 0. And this is x and this is y. So we get 0 and then we get cosine cubed t. And then we take the velocity, which is minus 3 cosine squared t sine t, and 3 sine squared t cosine t. Just write this again, 0 to 2 pi. And then we get cosine to the 4t. I think you remember that. I think there was an integral you have maybe in good memory when you were working on homework. And what is the key to do that? What is the key to do this integral? Wolfram alpha. Yeah, that's what I was actually told by the CAs. And about 90% of the class would always just plug that in directly in Wolfram alpha. And that's okay. I think it's really the most efficient way to do that, but you don't have that in the exam. So what do we do? Double angle formulas. Let me just remind you a little bit about double angle formulas. They really are handy. And so double angle formulas there are just two formulas which you have to remember. And one is to get cosine square t. What is it? Cosine 2. Yeah. And then the sine square t. 1 minus. And then there is another one which is actually useful. Cosine t sine t is also a useful one. What's that? Sine 2t half. By the way, you could get this one. You could get this one by differentiating that one. But these are the three formulas which are useful. And in this case, you could just now, the best way to do this is maybe write this as there's a cosine square sine square t, which you see here, which is actually sine square 2t fourth. And then we have a cosine square t, which we have 1 plus cosine 2t. So that's it. Now we are almost there, right? Because we have two integrals. One integral which is sine squared 2t, and one integral is sine squared 2t cosine 2t. The integral cosine squared 2t cosine 2t gives you sine cubed 2t over 3, and that goes away. So the only thing which survives is really 3 times the integral from 0 to 2 pi sine square 2t half dt. And you know that this integral is the same thing when you have cosine square, so you could use the double angle formula again, but you know it's just, this you know, it's just gives you, when you integrate that, gives you pi here, so this is equal to 3 pi half. So double angle formulas are your friend, and it's actually not so complicated. These are the three formulas which you have to know for integration purposes. And then there is another one which is useful, which follows from this. If you forget cosine square plus sine square t, you can actually read it off from here. Cosine square plus sine square is 1. So that's pretty cool. So that's actually kind of really helpful. That's a prototype problem. I repeated it. I know it's a very important type of problem. And let's look at the problem, this problem here from Switzerland. So I try to put a little bit of Swiss flavor in that lecture. And so we have a Swiss curve here. So this is an example where we want to compute the line integral, but it would really be tedious to compute this line integral. Right? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 curves which we would have to parameterize and then compute all these integrals. That would be awful. And so it's much better to use Green's theorem here. So this is a closed curve. And what is the curl? So first of all, we have to kind of think about what is the curl. Actually, it's always a good idea to ask what is the curl. Because if the curl would be 0, then the answer would be 0, would be conservative. What is the curl? In this case, I think it's simple. Is it 0? I didn't want it to be 0. Maybe I made a mistake. So it's qx minus py. That's the formula. So what is qx minus py? Qx, so qx is equal to 1 plus 2y cosine x, and py is equal to 2y cosine x plus 3. And if you take that away from each other, subtract that, so qx minus py is equal to minus 2. So what is the answer? Negative 10. So just, again, I warn you, don't just put the answer. Even if it's simple as that, don't put just the answer. So the answer is, by Green theorem, a line integral f dr is the double integral over the region curl of f dx dy, which is the minus 2 dx dy. And if we integrate minus 2, we can take it out. That's just minus 2 times the area of G, which is in this case 245. So it's minus 2 times 5. It's minus 10. Good. By the way, in this case, you would really have had a lot of trouble to compute this line integral. But it would be possible still with some a trick. You could easily change this, make it much harder by adding something crazy to make it impossible. So that's the typical Green application. These two examples are really typical for Green. George Green, Miller, self-taught mathematician. So this is his mill, and a little bit like Good Will Hunting. Stokes theorem, that's the third theorem already. I think we are in time. So this is the hardest problem because a lot of things come together curl, we have line integrals, we have flux integrals, we have surfaces, we have curves, we have lots of things. And so it deals with two geometric objects. One is a surface, and the boundary of the surface is a curve. And again, these two are linked by orientation. So the surface should be to your left when your head is up and you're moving forward. So in this case, that's a typical situation where you just, when this is the surface, you move, and your left foot is always on the surface, and you're going around the surface so that your head points in the direction of the RU cross RV. So that's a theorem, and again, this theorem can be used in both ways. You can use it to compute the flux, complicated flux integrals, or you can use it to compute complicated line integrals. And a special case is when the curl is 0, right? If the curl is 0, then we see that the line integral is 0. We have the closed loop property, and we get the gradient field if the vector field is if the region is simply connected. So that's one application. But by the way, this theorem has been found or kind of developed for an exam, like here, that was Stokes who gave that exam, multivariable exam, and that was problem 8, was to prove the Stokes theorem. And Maxwell, who developed the Maxwell equation, so he actually was a student who took that. So let's look at two problems. So the first problem deals with an awful surface. So the surface is given here as a parameterization. It looks awful, a little bit like a, I don't know. And so it's a parameterization, and then we have a vector field, and the problem asks you to compute the flux of the curl of the vector field through that surface. And if you hear or read flux of the curl, that's always a sign for Stokes theorem, because Stokes theorem deals with the flux of the curl. And so in this case, so we have to compute the flux of the curl of this vector field. Don't compute the flux of the curl of the vector field. That would be impossible. Instead, we just compute the line integral. So in order to compute the line integral, we have to first get the parameterization of the curve, the boundary curve. And the parameterization gives you what the boundary is, right? It's either s equal to pi half or s equal to 0 are boundary, but it turns out, and that's given actually, s is equal to pi half gives you the boundary. S equal to 0 is on the top of this surface. And so what do we do? So instead of computing this flux of the curl, which would be terrible, we compute instead just the line integral along the boundary. And so the boundary is parameterized. So the boundary curve is obtained by putting just pi half into the formula. So if you put pi half, we get r of t is equal to cosine t. And then pi half again, we get sinus t. And the third one, when s is equal to pi half, that gives 0. Cosine pi half is 0. Cosine 3 pi half is 0. So that's just equal to 0. So the picture really already tells you that's the rim here. And we also have to check that this is really the right orientation. But the orientation is given here. So that works. So let's count if you go in the right direction. And so we have just to compute the line integral instead. So we integrate from 0 to pi. And then we take the vector field and we evaluate it at this point, x, y, z. So we take f at, what is that? So we take x is equal to cosine t plus z y to the 9th, that's 0. The z, that's also 0. And the third one is also 0. So that was pleasant here. The vector field is quite simple on that curve. And then we have multiply this with minus sinus t cosine t. 0. So that's integral from 0 to 2 pi minus cosine t sine t dt. Today everything is 0, unfortunately. So we get cosine squared t half from 0 to 2 pi, which is equal to 0. So this flux is, the flux of the curl is equal to 0. That's a typical Stokes problem, where we have computed a flux integral. About orientation, maybe I just should say about this. This is a complicated surface, very familiar to you, this trouser, and so you have the task to find the orientation. So if the orientation of the surface is outwards, then what is the right thing? Is this really right here? If you go here along the belt, do we really go to the... It's correct, because the surface is to our left. And on the bottom, you see that also here, if you go like that, and our head is upwards, so we go in that direction. So that's the right orientation for that. And because it's not quite politically correct, I put some pants on here. So let's look at the new problem here. So find a line integral. It's a problem where we have to find a line integral. And along the boundary of a surface. So actually, that's kind of this picture here, right? Now let's think. So there is a surface given here, which is this cone, v cosine u, v sine u. So that's this surface here. But we want to compute the line integral here. Shall we compute the flux of the curl of f through this surface? That would be Stokes would suggest that. But who tells us that we should take this surface? I mean, any surface gives you the same result, right? So we take the same orientation than there. So let's take instead, this is the same thing. So we just take r of u of v is equal to, what is it, v cosine u, 0, v sine u. And so we take u from 0 to 2 pi and v from 0 to 1. So this is also has the same boundary. The advantage of this here is that we can really see we have the same Ru cross Rv. We have to compute this. It's minus v sinus u, 0 v cosine u, and cross of cosine u, 0 sine u. And then we see that we see the sign. What happens here? This is actually 0. This is minus v, and this is 0. So we see that actually the orientation was like before. It was pointing to the left, and actually the orientation is so that the normal vector is like that. And we take, instead of this surface here, we take this surface, which is a little bit simpler. And we have already computed Ru cross Rv. And we have now to take the curl of f and compute the flux integral. So we cannot avoid now computing the curl, but that's good. So we have the curl of f. Curl of f, let's just see, x, y, xy, dx, dy, dz. Curl of f is equal. What do we get? First component is x minus 0. Second component is minus y. And the third component is 0. So that's the curl. And we have already this, the parameterization of the surface. And we can now compute the flux. So the flux goes, the v goes from 0 to 1. And the u goes from 0 to 2 pi. And we take this x, we take the curl of f of r of u and v. What is that? So we take r of u of v is here, that's x, that's y, that's c. And then the curl of f, we take x, which is v cosine u minus 0, 0. So we take this, the curl evaluated on the surface, and this is the Ru cross Rv. So we take the dot product, and we see that this is nicely 0 here. V cosine u 0, 0 times 0 minus v 0. That's equal to 0. So today a lot of things are 0. So the answer is 0. Okay, let's step back a little bit. Just what happened here? We could have also computed the flux through this surface. Just take the original parameterization here and compute it instead. But that would have been a little bit more work. It doesn't really matter which surface we take. Yeah.
How do we tell if the orientation is right?
The orientation, yeah, that's what I was struggling with that a little bit too. And what happened is the problem actually doesn't give you the orientation except that it tells you the orientation of this surface. So the compatibility is already built in. So that's why I originally wanted to simplify it with another parameterization. But with this parameterization, you automatically have the right orientation because it gives you the orientation. So finally, that's the last theorem, the divergence theorem, which deals with divergence and has been found by Gauss or also Green. And so that's the theorem. It links a triple integral with a flux integral. And again, you can use it both ways. You can compute triple integrals, some triple integrals easier. But much more often it's that you want to avoid computing fluxes. And that is the link which does that. Let's just take this example here with a beautiful truncated dodecahedron. And so find the flux of the vector field here through that dodecahedron. You can, if you don't have even to write anything, what is the answer? Why is it 0? The divergence is 0. You see immediately the divergence is 0 here. This is the derivative with respect to x is 0. The derivative with respect to y is 0 of the middle term. The derivative with respect to z is 0 of the third term. This is 0, and so the answer is 0. By the way, this truncated dodecahedron has appeared in a project here, which is a pretty nice picture, kind of using different parts of built-in things. I kind of interpreted that, you know, this dodecahedron defend the tree from the dinosaur to be eaten. So I think that's kind of a nice interpretation. So, you can also compute fluxes through complicated surfaces like this one or this cheese here. By the way, this cheese, whenever I'm walking across the bridge, you know, there's this graduate school dormitories, I think. So this is kind of, it always reminds me of cheese here. So I'm a Swiss. So let's look at, so we have some Toblerone still here. This is a Swiss cheese. Find the flux of the vector field through the solid bound by the surface S. First who has the result gets some Swiss. So yeah, let's just see whether you're right. Yeah, what was the divergence? What is the divergence of F? So the divergence is 2, right? So we can do that here. So the divergence of F is 2. So that integral here of the divergence of f, that's just 2 times the volume of f, volume of the cheese. And this is a half ellipsoid. What is the volume here? So we have for a sphere, we would have 25 third pi 2 times 2. I think there is a factor 3 here, right? So 100 pi third. I think that's what it is, right? So the ellipsoid, when you because it's 5 here, you multiply the volume by 5, multiply the volume by 5, that gives you 25. 4 pi third. Oh, and then divide by 2, right? Because it is. Oh no, the 2 is here from the. I think that's correct. But you definitely got closest. You got closest to the thing. So I mean, it's just a volume computation, and the volume of an ellipsoid we know it's 4 pi third a times b times c. So it's 5 times 5 times 1. Good. So actually, there's another chocolate to give away here. What is the flux of this this vector field here through this? Who said pi? Did you already get the chocolate? You got already a chocolate. So you didn't get a chocolate. Yeah. Okay. Then you get it. So why is it pi? Yes, that's good. So actually, what happens is the divergence is 0, so the flux through the bottom part is the same as the flux through the bottom. The bottom part is the same as the flux through the top part, and so it's just the flux of this vector field through this, which is just the area times 1, which is pi. These are the derivatives. So we have the curl, the divergence, and the gradient. This triangle really kind of gives the picture very well. So from scalar fields to vector fields to scalar fields to vector field to vector field to scalar field. It's really a nice triangle. And also for integrals, we have the same triangle. There is in single variable calculus, in 2 dimensions, we have the line integral and double integral. In 3 dimensions, we have the line integral, flux integral, and triple integral. And it's always this triangle, and it's so important. It's even you find this in on the dollar bill, right? This triangle. So you just the gradient and the curl and the divergence are missing, but and even on the Matterhorn. So by the way, the Matterhorn is on this chocolate, and do you see? There is another thing hidden in. Do you see the bear? So that's the bear. And 2 important identities, divergence of curl is 0 and the curl of the gradient is 0. And these are you have that on the sheet. All these integral theorems are nicely organized here. Just very quickly about the decision tree. What integral theorem to use? This is an important slide. First, always ask yourself, is it a gradient field? Is it a gradient field? If it's a gradient field, then you use the fundamental theorem of line integral. If not, then you ask yourself, is the curve closed? If the curve is closed, then you can use Green or Stokes, depending on the dimension. And if not, then you are forced to do it directly. The decision tree for flux integral is very similar. You ask yourself, is it the curl of another vector field, or do we directly deal with the curl? Then yes, you use Stokes' theorem. If not, then you use you ask yourself, is the surface closed? If the surface is closed, you can use the divergence theorem, and otherwise you can do it directly. So these are all the objects. We have seen that, so these are the people kind of with a timeline who have worked on this. Ostogradsky is maybe a little bit forgotten, and that's green here. And here are more mathematicians who were working on this